Hi, I'm Dan LaChapelle, a graduate student in aerospace engineering at the University of Texas at Austin and Todd Humphrey's Radio Navigation Laboratory. This is Orbital War Driving, assessing transient GNSS interference from low Earth orbit. Global Navigation Satellite Systems, or GNSS signals, are relied upon by many safety-critical applications where there is a need for localization or clock synchronization. Due to the low strength of these signals at point of use, they are easily overwhelmed by RF interference, be it malicious, unintentional, or even natural in origin. This interference generally manifests itself in two forms, jamming and spoofing. Jamming is the simplest and most common form of GNSS interference. It usually entails broadcasting a narrowband waveform in navigation bands for denial of services. On the other hand, a transmitter spoofing a GNSS signal broadcasts a counterfeit signal intended to deceive the recipient into thinking it is authentic. In between these two techniques, you have matched code interference. That's when a GNSS satellite's pseudorandom ranging codes are broadcast sans navigation message. This is intended to fool receivers into acquiring the signal, but deny them a navigation solution. The work I'm presenting follows up on an earlier study by some of my colleagues that examined a different portion of the same dataset. Looking at years of carrier-to-noise ratio data in aggregate, along with the serendipitous raw data capture, the authors of that work were able to identify interference hotspots across the globe, recognizing that the International Space Station could potentially overfly a given interference source multiple times per day. We set out to expand on this work by attempting to detect interference over the equivalent of a single ground pass using higher rate data. The metrics that can be used to detect GNSS interference vary depending on the capabilities of the receiver. The ones listed here can be leveraged by many commercial-grade receivers, and depending on the kind of interference, these metrics may be more effective when combined. Some of the metrics listed here are more useful for discovering if your receiver is the target of a spoofing attack. For example, spoofing may be observed as an increase in the total received power, or a distorted correlation peak if your receiver is in danger of tracking an inauthentic signal. Neither of these metrics is particularly relevant to the International Space Station in low Earth orbit. The high Doppler shift and path losses of terrestrial signals makes them difficult to acquire, unless you're really trying to. The data downlinked from the receiver is rich. In addition to the standard PNT solution and reported quantities like the carrier-to-noise ratio, available at 1 Hz, we have access to 100 Hz data-wiped in-phase and quadrature accumulations, or IQ data. This higher rate can effectively provide more evidence for the presence or absence of GNSS interference. The ISS wheels around the Earth every 90 minutes at 420 kilometers altitude. Spacecraft in low Earth orbit have considerable utility for detecting terrestrial GNSS interference, chiefly because they are close enough that the malicious signal can be seen, but far enough away and moving quickly enough that it doesn't have the chance to do much harm. Depending on the location of an interference source relative to the ground track of the ISS and local topography, it may be possible for it to be visible for several minutes. Back in the day, before Wi-Fi was ubiquitous, enterprising would-be wireless internet users would have to find and record the locations of wireless access points. This task was easiest accomplished when facilitated by an automobile, especially when you take into account the bulky consumer electronics of the day. I'm stretching this concept to include low orbit. In this metaphor, the ISS is our trusty car, and the FOTON receiver our laptop. The orbit of the ISS over time enables us to survey much of the Earth under 51.6 degrees latitude. Note that due to the orientation of the antenna looking rearward, an interference source is most visible after the ISS has flown over it. The receiver hardware in question is FOTON, the Fast Orbital Tech, Observables, and Navigation Dual-Frequency GPS Receiver. It was launched to the ISS in 2017 as part of the Group C experiment to characterize the ionosphere by way of GPS radio occultation and UV photometry. Group C is in turn part of STP-H5, an unclassified DoD Space Test Program payload mounted on the ELC-1 platform. Photon's antenna faces aft, opposite the direction of motion of the ISS. In addition to the standard 1 Hz observables and 100 Hz IQ data, Photon is capable of short-duration raw data captures at 5.7 megasamples per second, limited by onboard storage and downlink capacity. It was this capability that was exploited in my colleague's prior work to analyze a serendipitously captured interference signal. Outside of a relatively narrow cone centered on the antenna's bore site, incoming GNSS signals are likely to be obstructed or subject to multipath due to the changing geometry of the space station's radiators and solar panels. In-phase and quadrature, or IQ data, result from modeling the received signal as a complex phasor. The 100 Hz IQ data can be used to compute the carrier-to-noise ratio at a higher rate and level of resolution than is typically reported by the receiver. But if the phase error is approximately zero, that is, the quadrature component is just zero mean noise, it's possible to use the in-phase component directly as a substitute for carrier-to-noise ratio. Recall that most of the signal's magnitude and therefore power is contained in the in-phase component. Again, the primary benefit of using the I component is the higher rate, which allows us to build up more evidence for possible interference events. The I component does also possess some advantage as a detection statistic over carrier-to-noise ratio. That is, its use can yield higher detection probabilities for a given false alarm probability. However, this advantage is really only noticeable for very low carrier-to-noise ratios. GNSS interference as seen from low Earth orbit, particularly matched spectrum interference, tends to resemble multiple axis interference. The carrier-to-noise ratio in the presence of interference becomes the carrier-to-interference in noise ratio. The effect of interference depends on its spectral shape and on the shape of the local code replica. The interference signal's equivalent noise density I0 is proportional to its power Pi multiplied by the authentic signal spreading code chip interval Tc. There is a catch. The RF front-end's automatic gain control, AGC, ensures that the total received power is held constant, but the AGC gain isn't reported by the receiver. We can infer the value of the AGC gain by comparing measurements assumed to be without interference to those in which the presence of interference is possible or suspected. The statistical decision framework we use to find possible interference events is transient change detection, or TCD, a family of approaches to detecting a statistical change in a random series that is closely related to quickest change detection, or QCD. One twist in our scenario is that the cardinality of the data at each measurement epoch abruptly changes every now and then as GPS satellites enter and leave the field of view. Pictured is a simulated example of what some of this variable cardinality data might look like. The approach boils down to comparing a windowed sum, or finite moving average, of log likelihood ratios to a threshold. This threshold is computed from the statistics of the series under the null and alternate hypotheses, along with the desired false alarm probability. And here's our approach applying to the simulated data. The change event is clearly visible in the finite moving average detection statistic. Of course, reality is never quite as benign and well-behaved as the example presented here. Recall that the goal of this work is to catch GNSS interference in the wild over the equivalent of a single ground pass. Here's an example of an interval of data discovered by the approach presented that appears highly suspicious. As you can see, the IQ data shows a substantial decrease from nominal in the I component, during which the GPS satellite ought to have been squarely within view. I consider this smoking gun, so to speak, to be the sharp recovery at the end of the interval. This could be the point at which a terrestrial interference source would disappear behind the curve of the Earth from the point of view of FOTON. Note that the Black Sea region would have been visible during the interval. There are numerous reports of GPS interference in the region affecting commercial shipping. A similar profile was identified over an interval that suggests interference originating in North Africa or the Mediterranean. Numerous GPS disruptions reported to the U.S. Coast Guard's Navigation Center suggest significant interference events of unknown origin in the vicinity of Libya. The strongest and most consistent interference over the 3-year period studied by Murray et al. Was located in the eastern Mediterranean. Clever processing of a raw data collection was able to geolocate it to Khmeimim Air Base in Syria, the center of Russia's military presence there. GNSS jamming and spoofing was most likely deployed there to thwart drone swarm attacks, which have occurred a number of times since January 2018. This work was enabled by the DoD Space Test Program and supported by the U.S. Department of Transportation and the University of Texas Wireless Networking and Communications Group, WNCG. A next step in this work would be to apply this detection approach to even more of the multi-year dataset and compare the survey results with the prior work. A more effective low Earth orbit interference detection platform could be a standalone satellite without the challenging blockage and multipath environment of the ISS. Using an approach like the one presented here, such a spacecraft could even autonomously initiate a raw data capture when anomalous measurements are detected for further analysis on the ground.